Hello everyone, Kotongwane, the native god here. Right, today we'll be looking at a topic under kinematics for engineering science and for called resulting velocity. Right, if you're watching this video, I would imagine you've already gone through relative velocity. Right, because remember under kinematics you get three sections: relative velocity, resulting velocity, and then projectile motion. Right. So if you're watching this video, I would imagine you've already gone through relative velocity. It is going to make things much easier if you have seen that we'll be applying more or less the same principles that you applied in relative velocity, right? With a slight twist, of course, right? Now, under resulting velocity, we're essentially looking at the resultant of the vectors acting on a certain object, right? We are essentially going to calculate the resultant velocity, right, based on the case that you are looking at. Now, I say based on the case you're looking at just because under resulting velocity, we essentially get two cases, right? One case, you will be asked to simply calculate the resultant velocity, right? They simply give you the original velocity of the object you're looking at, be it a boat or plane, right? You're given the original velocity of the object, right? And then you are also given a wind vector, right? And then you are simply asked to calculate the resulting velocity as well as the direction thereof, right? That one is pretty simple, pretty straightforward, right? That's case number one. So case number one, you'd be given, say, the original vector of the object, right? Be it a boat or whatever the case may be, as well as a wind vector, right? And then you would use those vectors to calculate the resulting or the resultant velocity, right? That's case number one, pretty straightforward, right? And then case number two is where you are essentially told that direction, right? You are told the direction in which the object, for instance, an aeroplane, you are told the direction in which the aeroplane must take, right? Thus, essentially giving you the direction of the resultant, right? So case number two, you are essentially given the resultant, or at least the direction of the resultant, right? And then maybe you are given enough information to be able to calculate the resultant, and then you are asked to calculate what is this? Say maybe the original vector of the aeroplane, right? As well as the direction in which the aeroplane must take in order to get to that direction that it is intended to go, right? So essentially, that will be your two cases. Again, one case, you're simply given the original vector as well as the wind vector, and you're asked to calculate the resultant or resulting velocity. And then case number two, you are told where the aeroplane or where the object, right, the direction in which the object must take, right, must here being the operative word, right? You are told the direction that the object must take, right? Essentially giving you the direction of the resultant, right? And then they maybe ask you, to calculate the original velocity of the object, right? And the direction in which the object must take in order to end up in the direction it is intended, accounting for, of course, the wind vector, right? This is all going to make sense when we look at a couple of exercises, right? Now, for this lesson specifically, we are going to look at case number one, right? So case number one being, if you look at question 2.1 here, right? They said a plane takes off from Wonderboom Air Base in a direction north 40 degrees west at a speed of 360 meters per hour. It is then blown off course by a wind of 120 kilometers from a direction west, 30 degrees south, right? So we are given the original vector of the aeroplane, right? And we've of course given the wind vector, and the question is determine the resultant velocity with its direction, right? So like I said, first case, right, you are essentially given the original vector of the object as well as the wind vector, and you are simply asked to calculate the resulting velocity, right? So this is case number one, which is what we will look at on this lesson, right? So let us represent the vectors on a Cartesian plane, right? So just like in relative velocity, we use essentially two methods, right, in calculating what we need to determine, right? You either use the method of components, right? Method of components, right? As well as what is this? You can also use the parallelogram method, right? Now, for the first two videos, right, on this playlist, I'll be looking at first we'll look at the two cases, right? So for both cases, we are going to use the method of components, right? And then in the videos that will come after that, we'll then look at the same questions but now using the parallelogram method, right? So again, first I want us to look at the two cases, right? This video or this lesson is based on the first case. The second video on the playlist will be based on the second case, right? For both videos, we will use the method of components, right? And then from the third and fourth video, we're going to be looking at the same problems, but now using the parallelogram method, right? Now, let us represent this, the vectors on a Cartesian plane, right? Right. Okay. Right. Now, we have, based on what we've given here, they said the plane takes off from 1A base in a direction north 40 degrees west, right? So the plane is going, takes off and goes in a direction north 40 degrees west at a speed of 360 kilometers per hour, right? So we take that as the original vector, original velocity of the airplane, right? So that is regardless of the wind vector, right? So this is going in a direction north 40 degrees west at a speed of 360 kilometers per hour, right? So we are given the original, we're given the original wind vector, right? So the original wind vector we are going to denote as V sub O, right? So essentially meaning V sub O, which is the original vector, right, is for this case 360 kilometers per hour, right? Now it is going in a direction north 40 degrees west, right? So that would be north 40 degrees west, right? So this original vector is on this quadrant, right? North 40 degrees west. That means our angle is referenced from the y-axis, right? Remember that regarding direction, right? The first direction pertains to where this angle is referenced, right? And the second direction pertains to where the object is going, right? So north is the reference for this angle, so meaning the 40 degrees is a reference from north, right? And the plane is going west, right? So north 40 degrees west, so that would be, say, in this direction, right? Now, in method of components, I always advise students to reference their angles from the x-axis, right? That is to make sure that when resolving your oblique vector into its components, the one that is in the x direction will be in terms of cos, and the one in the y direction will be in terms of sine. So in terms of sine, so meaning your vertical component, right? In order for your vertical component to be in terms of sine, and your horizontal component to be in terms of cos, your angle has to be referenced from the x-axis, right? So seeing that the angle that you've been given is referenced from the y-axis, right? We then get the one that is referenced from the x-axis, right? So if this angle is 40, we know this entire angle is 90 degrees. So meaning this angle will be 90 minus 40, which is 50, right? This here, this is VO, right? This vector is, this is our VO, right? It is our VO, right? So to get, or maybe let us write down the value of this, right? Let us write down the value of this. So VO is equal to, VO is 360 kilometers per hour, right? Let's make this one a bit bigger. Right, so that's our VO. Right, that's our VO. Right, VO is going in that direction, right? Now, as is evident, VO, the original vector, is oblique, right? And remember, in method of components, in order for us to be able to apply conditions of equilibrium, right, we need to have vectors that are parallel to the Cartesian plane, be it parallel to the y-axis or parallel to the x-axis, right? That is why oblique vectors we need to resolve into its components, right? So we are going to need to resolve these vectors into its components, right? So resolving the vectors into its components, right, we're going to have a vector that is parallel to the y-axis and one that is parallel to the x-axis, right? So essentially this one becomes VO in the y direction, which is equal to, so because our angle, the angle we're going to use is reference from the x-axis, right? So the 50 degrees, it means our vertical component will be in terms of sine. So this will be 360 sine 50, right? And then as far as the horizontal component of VO, right, this will be VO in the x direction, right? Again, because we're looking at the horizontal component, right, and our angle is referenced from the x-axis, the component in the x direction, the horizontal component will be in terms of cos, right? And then of course you have to consider the direction. This is going west. West we take as negative, so this will be negative 360 cos 50, right? And this becomes here our VO in the x direction, right? So we are done with resolving the original vector. Now we look at the wind vector, right? They said the wind, it is then blown off course by a wind of 120 kilometers per hour, right? From a direction west 30 degrees south, right? Now with the wind, it is very important you take note of the direction of the wind, right? Now in this case, they've made things very easy for us. They told us that this wind vector is coming from a direction west 30 degrees south, right? So because it is coming from this direction, it means it is going in a direction essentially opposite this one, right? They said it's coming from west 30 degrees south, right? So because it's coming from this quadrant, it means it is going in that quadrant, right? So you always draw, as far as your wind vector, you have to always draw it in a way that is going away from, right, away from the point of intersection, right? So the point of intersection being the center of the Cartesian plane, right? If you draw it in the third quadrant, right, seeing that they said it's coming from west 30 degrees south, it means if you draw it here, it will be in that direction, right? And our vectors always have to be such that they are going away, right, from the center of the Cartesian plane, right? So meaning, seeing that this is coming from that direction, it means it is going in this direction, right? So what is this? So opposite of west is east, 30 degrees opposite of opposite of south is north, right? So this is going east 30 degrees, right? 30 degrees. Let me change the color of this, right? 30 degrees north. So we have 30 degrees there. This is going in this direction, right? This we can call the wind vector. So the wind vector is denoted as just simply VW. So VW is 120 kilometers per hour. So this is 120 kilometers per hour, right? As again is evident, the wind vector is oblique, right? So we have to resolve it into its components in order for us to be able to apply conditions of equilibrium, right? Right, now resolving this into its components, you're going to have the vertical component as well as the horizontal component, right? Our angle is referenced from the x-axis, so our vertical component will be in terms of sine, horizontal component will be in terms of cos, right? This is going, so this is VW in the y direction, so this one is 120 sine 30 degrees, and then we also have VW in the x direction. It is going east, so it's going to remain positive 120 cos 30 degrees, right? Right, so these are the vectors we have. You have the original vector as well as the wind vector. So now we'll be able to calculate the resulting velocity using the method of components, right? Now, method of components. Right, using the method of components, right, we are going to calculate the sum of velocities in the x direction, right? So this is one of the conditions of equilibrium, right, that we are able to apply, seeing that our vectors are now parallel to the Cartesian plane, right? So this will be Vox plus VW in the x direction. And what is this equal to? VOS is negative, so this is negative 360 cos 50 plus VWX, which is positive 120 cos 30, right? Now if you punch this in your calculators, you're going to get negative 127,480, right? Maybe not write the kilometers here. Now seeing that this is negative, right, that speaks to the direction that this vector is going, right? So seeing that we are looking at a horizontal or a vector in the x direction, or the sum of vectors in the x direction, right? The negative is basically telling us that this vector is going in a westerly direction, right? So you rewrite this as positive 127,480 kilometers per hour, right? and the negative indicates direction. Direction is west, right? So once you've accounted for this negative sign by saying that the negative sign actually means this is going west, right? You are not going to have to use this as negative in any of the calculations, right? So now we look at the sum of velocities in the y direction, right? This will be equal to VOY plus VWY, right? VOY is 360 sine, right? This is 360 sine 50, right? Plus VWY, which is 120. So that's 120 sine 30, right? And this one is equal to, now if you punch this in your calculators, you're going to get 335,776 kilometers per hour, right? And because it's positive, right? So because it's positive and we're looking at the sum of vectors in the y direction, that is an indication that this is going north, right? That is going north. So now you've calculated both the sum of vectors in the x as well as sum of vectors in the y. Now we can calculate the resultant velocity using Pythagoras, right? So in using Pythagoras, we are then able to calculate the resulting velocity. And this is how we denote the resultant velocity. V sub r, right? So this will be the square root of sum of Vx squared plus sum of Vy squared, right? So this is equal to right. So now we substitute sum of Vx. Sum of Vx is 127. So this is 127, 480 squared plus sum of y, which we calculated and got 335,776 squared, right? Right. Now, if punching this in your calculators, you are going to get, so the square root of all this is going to be equal to 359,161 kilometers per hour, right? And that becomes the magnitude of the resultant velocity, right? Now we have to calculate the direction, right? Now the direction side of things is pretty straightforward, right? As I've mentioned, that to make things easy for ourselves, we should always reference our angles from the x-axis, right? So we are going to do the same with the resultant velocity or the direction thereof, right? So in calculating the direction, we simply use tan theta is equal to, right? Now, for the angle that we're going to calculate here, for this angle to be referenced from the x-axis, right, tan theta will be equal to the sum of v in the y direction divided by the sum of v in the x direction, right? So taking this approach means that this angle is referenced from the x-axis, right? If our angle was going to be referenced from the y-axis, then this would have been the approach. This would have been sum of v in the x is equal to, divided by the sum of v in the y direction, right? Right. So again, we use this because we want our angle to be referenced from the x-axis. And our angle being referenced from the x-axis, this is the approach you would take, right? Right. Also, this one is the one that happens to appear on your formula sheet, right? Right. Now let's calculate our theta. Calculating theta, this will be arctan of sum of v in the y direction, right? Sum of v in the y direction is, what is this thing? Sum of y in the y direction, sum of v in the y direction is 335,776. This divided by sum of v in the x direction, which is 127,480, right? And then punching this in our calculators, right? So punching this in our calculators, we get arctan of 335,776 divided by 127,480. So this becomes 69,210 degrees, right? Now you can write down the resulting velocity. So resulting velocity essentially is equal to, the magnitude is 359,161 kilometers per hour, right? Now for direction, right? The way we calculated theta is such that theta is referenced from the x-axis, right? So our theta being referenced from the x-axis, right? So remember, as far as direction, what I said to you, right? The first direction gives us where the angle theta is referenced from, right? We've already established that our angle is referenced from the x-axis, right? Now between the two components, which one represents x? This one represents x. So essentially our angle theta is referenced from west, the x-axis, which is west, right? So this angle will be west. The angle itself is 69,210 degrees, and this is headed north, right? And this would be your angle, right? Now, had you reference your angle from the y-axis, right? Essentially, what it would be 90 minus what we got, 69,210, right? Which is 20,79. Right, so had we reference our angle from the y-axis, it would be, that would still be the magnitude, right? And then as far as direction, right, so theta reference from the y-axis would be equal to 90 minus 69,210, which is 20,79 degrees, right? Or you could have used what is this, tan theta is equal to the sum of v in the x divided by the sum of y, right? And then if you used this is what you get, right? So you essentially get the same thing, right? So if our angle was referenced from the x-axis, from the y-axis, right? The y-axis between these two is north, so that would mean this is going north. The angle reference from the y-axis is 20,79 degrees, headed west, right? So both answers are acceptable. So you would either have this or that. But again, to make things easy for ourselves, always reference your angles from the x-axis, right? Right, and that is how you would approach such a question, right? So this is the first case under resulting velocity, right, where you are just given vectors and you are asked to calculate the you are asked to calculate the resulting velocity, right? In the next video, I'll be explaining the second case, right? Good luck to everyone. Goodbye.